Welcome all the course participants. As has been told to you, today we will be having a kind of experiment extracting information from satellite imageries. So again, this will be a hybrid mode. We will do something in visual theory, how to extract information from satellite imageries, and then we will see the experiment, how to extract the information from satellite imageries. So the content or the presentation outline would be, we will see how a satellite imagery is captured, though it has been told earlier also, just a revisit to how the imagery is captured, what are the various characteristics of those imageries, and then coming to our main topic, reading the satellite imagery visually as well as in the digital image analysis. So I'll start. So first thing is, we should define remote sensing. Like right now, all of you are doing remote sensing. Remotely, you are seeing the slides that are being displayed. Remotely, you are listening to the content. So all of you are remote sensors, right? But the term remote sensing was coined for gathering information about the Earth's surface by by measuring the portion of electromagnetic radiation, which is either reflected or emitted or backscattered from the Earth's surface. Right? So remote sensing, as in our everyday life, we use remotes, right, for gathering information or operating an object remotely. So here also we can say it is we are gathering information about the Earth's surface by measuring the portion of electromagnetic radiation which is reflected from the Earth's surface. Now, what is done here is there is an energy source in passive remote sensing. We use the natural energy source. During the day, we use the sun's energy. This energy is traveling to the Earth's surface. Then there is a satellite which is orbiting around the Earth. It has the sensors which is recording the portion of this reflected energy. And this satellite, it is orbiting around the Earth. Whenever it is in contact with any ground station, it transmits all the energy, all the information that it has recorded on board to this ground station. So from this ground station, the data is processed and it is given to the users for analysis, and subsequently the users can make certain decisions from this processed data, like we can make a land use, land cover map, a forest map, any particular theme can be generated from this satellite imagery. Now, we said there are satellites which are orbiting around the Earth. So there are two kinds of satellites which can orbit around the Earth. So satellites, so satellites, all of you know, they are objects which revolve around another object following a path which is known as orbit. For remote sensing, for the Earth observation, we are mainly having two kinds of orbits, geostationary orbits and sun-synchronous orbits or polar orbits. So geostationary orbit, like which is shown here in this animation, it is an equatorial west to east orbit, right, satellite which orbits around the Earth. It is launched at a height of about 36,000 kilometers. It is at this height that it makes the revolution in 24 hours, which is synchronous with the Earth's rotation. So in this way, a person who's standing on the Earth will feel that this object is, the satellite is stationary, because the satellite seems to be looking at the same area on the Earth, right? It always views the same area on the Earth. So normally the weather satellites, the communication satellites, they are launched in the geostationary orbit. Now we are talking about the sun-synchronous orbits, the polar orbits, which are capturing the periodic data of the Earth, right? So these sun-synchronous orbits, they follow a north-south orbit. They follow a north-south orbit. And the orbit is so inclined that when the satellite is moving from north to south and the Earth is rotating underneath, so combinedly it covers each area of the Earth at the same local sun time. And that is the reason it is called as sun synchronous. So this will ensure, similar illumination conditions, right? And mostly these satellites, they capture the data in the morning, somewhere between 9:30 to 1100 hours. You will see various satellites in this orbit in the varying altitude, somewhere between 700 to 1000 kilometers, with little bit inclined orbit, right? Orbital periods around from 90 minutes to 100 minutes and so on. And it crosses mostly the equator at the around 10:30 local time. Right? So there are large number of satellites and they make periodic coverage for, that means they're capturing the same area repeatedly. So we are mainly discussing the data captured by the sun synchronous satellites, right, about the Earth's surface. Now these satellites, on board they have sensors. The satellites are orbiting around the Earth. On board they have sensors which are recording this information. And the sensors which record the information, they have 4 characteristics. That means this characteristic is called resolution. That means the ability of the sensor system to record the smallest information. Now, smallest information in terms of size, that means the smallest thing it can capture. So high spatial resolutions, now we have resolutions available from 0.3 meters onwards, and we have low spatial resolution. That means the smallest area that the satellite sees on the ground, right? So you can see it is 0.3 meters to onwards, up to it can go up to 1 kilometer. Then the spectral resolution, that means the narrowness of the wavelength interval in which the satellite is capturing the data. Right? So in general, we can call it, in general terms, we can say, okay, how many number of bands that the satellite is capturing. Right? What is the utility of this band that we will see in this experiment that we see. Now the satellite can capture the various energies. Right? It can capture very dark areas, to dark areas, to bright and very bright areas, right? So minimum change in this DN value or minimum change in the brightness that can be captured by the sensor is termed as its radiometric resolution, or basically the quantization level of an image. Then it is the temporal resolution. That means how often the satellite can look at the same area, right? So when we can have high spatial temporal resolution, when the satellite can look on the same day at the same area, right? And medium to low temporal resolution. That means satellite comes at the same place after a long time, some number of days. So these are the 4 characteristics of the sensors which are on board these satellites. So with this basic information, now resolution, we said it is the smallest size that the satellite is looking on the ground, the smallest size of the object, or you can say smallest area that the satellite sensor is looking on the ground. Right? If you say technically, it is the smallest discretely separable quantity in terms of either distance, that means spatial resolution, or wavelength band, that is spectral resolution, temporal and radiometric resolution. Right? So here you can see this example. It's a coarser resolution when the satellite is the smallest area it can look is 1 kilometer. Right? So Indian satellites have the capability to map from the coarsest resolution 1 kilometer to a sub-meter pixel, to a sub-meter pixel. Like for example, there are the earlier popular satellites which we were working was the IRS 1A, 1B, right? LIS 1, LIS 2 sensor, LIS 3, list 4 now, right? So they are like list 2 is 36.25 meters spatial resolution. That means the smallest area it can look is 36.25 meter spatial resolution. 1C has list 3, which is 23.5 meter spatial resolution. The list 4 can look at a smallest area of 5.8 meters. And now we have Cartosat series of satellites which have varying resolutions from 2.5 meters to 0.3 or 2.6 meters. Right? Okay, so once the image is captured in different spectral bands, it is captured in number of spectral layers, then we can extract information either visually or by doing image processing. So when we do visual interpretation, it is called as image interpretation, and it is defined as act of examining images to judge their significance. Act of examining images to identify certain objects and judge their significance. So we examine an image to identify objects and judge their significance based on different elements of interpretation, which I have listed here, and we will be seeing them one by one. We identify objects based on their shape, based on their size, based on certain other information like shadow, like texture, like pattern, and so on. So what are these elements of interpretation? How they are useful in extracting objects and judging their significance? We will see them one by one. Okay, so first object that the first element of interpretation that we can see is the color or tone. Right? So tone basically refers to relative brightness or the color of the object. Like here you are seeing now a black and white image. Here you are seeing a black and white image. So it is basically a grayscale image. You are seeing some objects as very bright, some objects are dark. So objects which do not reflect energy are darker on this image, and objects which reflect more energy are brighter. And then there are some grayscale objects which indicate that they are reflecting less amount of energy than these brighter objects and more amount of energy than this darker object. So this is one element of interpretation which helps you identify various objects. Like now, our previous one was a grayscale image. Now you are seeing the colored image. So it is very easy to identify objects in color. It is very easy to distinguish objects which are having similar reflectances. Like for example, if I say these are similar reflectances, but in grayscale image, you will not be able to distinguish between the land use or the object. So in the colored image, when the tone is available in color, so it is very easy to distinguish between different objects. Like for example, you can see even in green color, we have two different shades indicating these are different objects or different land uses. Then the next element of interpretation is shape. We know that shape refers to the general form or structure or outline of objects. Right? So shape actually is a very distinctive clue for image interpretation. We can identify here different objects simply based on their shapes. Like for example, these vehicles. Right? So vehicles, the shapes are characteristic. The roads you can see. Now in roads also we are having two type of roads here. You can see here there's a bend, so that means and then you can see the shadow also and smoother bends. So flyovers, level roads, right? Elevated roads. All these can be extracted or their significance can be judged based on their shape in addition to other elements of interpretation, right? So we can identify some circular tanks on the top of the building, right? You can see the top circular tanks on tops of the building. So shape is one characteristic, right? What is their significance? That we can judge if we associate it with other elements of interpretation. Like if I use other elements of interpretation like shape, size, texture, pattern, association, I'll be coming to them one by one. So we can say that these circular tanks on top of this building may be some water tanks, right? As compared to when I come to the other imagery, I will show you other circular tanks. Okay, then size is another criteria. Size of objects is also one of the criteria to identify objects and judge their significance. So you can see here that in this particular image, I'm trying to show various aircrafts and their different sizes. They are different sizes. So all those who are in the aviation industry, by looking at the shape and the size of the aircraft, they can say whether it is a Airbus 320, 321, 737 Boeing, or even a helicopter, right? And so on. That can be judged by the shape of the aircraft and its size. Then pattern. Pattern is one other element of interpretation. Another element of interpretation which refers to the arrangement of the spatial arrangement of the objects, right? So we can say that if there is a repetitive pattern, and it will have a distinctive tone and texture. Like for example, here it is a pattern of orchards which is being shown here, right? An orchard will also have a pattern of roads in between, right? So that is a recognizable pattern which also helps in identifying various objects. Texture. Now, texture refers to the microtonal variation. Microtonal variation in a tone in a particular area. Like this is an example of pattern as well as texture. We can see a pattern of trees. We can see a pattern of trees organized with some rows or spacing in between, and we have the natural growing trees here. The natural growing trees have a natural pattern, and here it is a man-made pattern, right? Their texture also is different. Microtonal variation in the pixel intensity, that also differs in the plant orchard, or you can say the patterned areas, and natural vegetation. So this is a good example where you can see the example of different tones, texture, shape, size, right? And even patterns, somewhere patterns are also there, right? So now here you can see when I want to identify objects based on their tone or color, there is different shades of green. In different shades of green, you can very easily distinguish between the grasslands and the trees, because grasslands have a smoother texture, the trees have a rough texture, right? The microtonal variation is more in trees and it is less in the grassland. Even in grassland, you are seeing two kinds of tone, two kinds of colors. Then different objects like buildings are in different colors, the roads are in different colors, right? And the shape of the houses, the shape of the roof tells you whether it is a inclined roof or a flat roof, right? The little bit shadow, if somewhere it is there, it can tell you about the height of the building, the height of the trees, right? And so whenever we are extracting information, we use a mixture of, or you can say more than one element of interpretation for extracting different objects. So shadow, as I was saying, shadow is yet another element of interpretation which gives us an idea of relative height of objects. By looking at the length of the shadow, you can also judge the height of the objects identification of such objects become easier due to shadow. Like you can see that this is a very high-rise building with a very large shadow, right? And the height of this building is less than the height of this building because of its shadow being falling from the same angle. However, if you are seeing that this high-rise building has a very high shadow, it is obscuring the details which are there in the shadow area. So shadow becomes an aid in interpretation, also as a hindrance, because now it is obscuring the details in the shadow region, right? But it is good in interpreting the relative height of different objects. The other element of interpretation, okay, before that, another example, which like in the previous example, I told you that we are on top of a building, there were circular objects which we identified as the water tanks. Now, if we look at this imagery, these are also circular tanks. The shadow indicates that they're heighted objects, right? There is a pattern of them. There are 4 here, and there is a linear 6 tanks here. But now I would call them, they are not water tanks. The previous one, they were on top of a building. So being associated with building, we could say they are water tanks. But here, if we can see that they may be some storage depot, either oil storage depot or some chemical storage depot, and the number and the size may indicate it is a chemical factory or an oil storage depot, right? Based on the association. So here also you see different objects we are extracting based on the color, based on the shape, based on the size, based on shadows. Right? Association. Like in the previous examples, when I said circular tanks on top of a building are water tanks, and circular tanks in the previous one were oil storage tanks, right? So what we are taking basically, we are taking association into the account. Association is the relationship between the objects or features in their proximity. That means in the relative areas, in the background, right? So what is that is association, how the objects are related to their background. Right? So identification of a feature, one would expect to associate features that may provide information to facilitate identification. Like for example, if you are looking at this pattern, right? If you can judge, this is a railway station. This is a railway station with somewhere the trains are also on the track, right? And this particular linear feature is a road, and these features are the railway tracks. Right? These are the railway tracks. You can also see a different pattern of roads, right? A different pattern of roads as compared to the linear railway tracks. You can also see the footover bridges on the railway station, right? And some parking lots, right? Some parking lots. So different elements of interpretation, shape, size, tone, texture, pattern, association we are using to identify different objects, and we are judging their significance based on these elements of interpretation. Now the previous ones were some were the satellite imageries and some were the aerial photographs, right? Now this one particular imagery I have written is, it's a Cartosat 1 imagery of 2.5 meter spatial resolution. Now this is a single band imagery, a panchromatic imagery where we do not see colors, right? But the high resolution makes it evident to identify various agricultural fields, we can distinguish between the roads and the canal based on the tone, right? Based on the tone and the shape. The roads are more straight, right? They can have sharp bends also. There are more roads coming and joining the roads, right? And canals, if you see, they have smoother turns. They have smoother turns. Plus, canal has water, which is giving it a dark signature. Yeah, whereas roads are lighter as compared to your water. So we can clearly distinguish between even different type of roads, the highways and the major roads, minor roads, even the boundaries of the agriculture fields. They can be identified by the shape, size, texture, pattern. You can see also the urban areas, stadiums, right? In this cartosat imagery, which is a panchromatic imagery devoid of the color. Still, even in the agriculture areas, you can see that there are different shades of the agriculture areas. Somewhere they are very dark, somewhere they are very bright, right? So there are different interpretations of these areas. Now coming to the other imagery, the railway station which I showed you, right? Another example of railway station you can see here is the Hyderabad Nampalli railway station, and this imagery we have taken it from the Google, right? So you can see a pattern of railway tracks, and on some tracks the train bogies are there. You can see you can even count the number of bogies in a train, right? You can count the number of bogies, and you can also, even if you know the scale of the imagery, you can also calculate the length of each bogie and the length of the train. Right? You can see the covered platforms. You can also see the covered platforms and different shapes of the buildings, some high-rise buildings causing the shadows and some lower buildings, different shapes of the roofs, right? Different shapes of the tin roofs, flat concrete roofs, etc. Right? In the greens, you can see trees having rough texture as compared to the grasslands which are having smooth texture. Then there is a pattern of houses or a pattern of built up areas with a pattern of roads in between. So we are normally using more than one element of interpretation to identify an object, right? This may be the parking of the railway station. So association also comes into the picture, right? So this is okay. So that was an urban area. Now this is a mountainous area. In the urban area, you see a very straight pattern of roads, right? You will see a very linear pattern of roads. And in a mountainous area, your roads will be in a curvilinear feature or not straight roads. Right? So this is Mussoorie hill station near to the Dehradun, and you can see the roads leading to the Mussoorie. This is Mussoorie Lake, and you can see water is very dark because water reflects less energy and the greenery. So in a nutshell, we have used various elements of interpretation like shape, size, tone, texture, pattern, association, etc. to identify objects visually and judging their significance. We are using more than one element of interpretation. Now this happens when you are looking at very high resolution images, right? You are able to see different elements of interpretation. Now coming to various satellite imageries, like here multispectral imageries, satellite images are captured in many wavelength intervals, right? We are capturing the blue portion of the spectrum, green portion of the spectrum, red portion of the spectrum. And then when we generate a composite, it is called as true color composite. But satellites are capturing even beyond the red portion of the spectrum, that is in infrareds, near infrared, middle infrared, thermal infrared, far infrared, and then the infrared we cannot see with our eye. So then what we are doing is we are generating a composite where we are using the infrared portion of the spectrum, red portion of the spectrum and the green portion of the spectrum, the data which is captured in these, and then displaying a composite which is called as false color composite. Now you see that in true color composite, whatever colors we see on the ground, same are visible. But in false color composite, we are using infrared. Infrared we cannot see with our eye. We are putting infrared to the red channel of the monitor or the red color gun, and then stacking it with green and blue. The composite that we generate is called a standard false color composite. And if you look vegetation, or you can see forest, they appear red in color, right? Because vegetation reflects infrared very highly. So you will see the forest as red in color in a false color composite on a satellite imagery. Agriculture areas you will see in varying shades of red depending upon the height of the crop and the density of the crop. Water does not reflect infrared at all. Any reflectance that is there is due to the sedimentation or the phytoplanktons. So water you will see from dark blue to black, right? Depending upon the depth of the water and the sedimentation. Right? So this is regarding these are the low resolution multispectral images. So the fine geometry is not visible here. Now this is a Landsat thematic mapper image. This is a Landsat thematic mapper image. The spatial resolution is 30 meters. That means the smallest area that is visible on the ground is 30 meters. Here you can see two water bodies, two reservoirs in this particular image, which are having very dark color, black color almost. So these are two water reservoirs joined by a canal, Forest areas in red color, agriculture areas in varying shades of red. Somewhere where the crop is not there are also greenish, bluish greenish in color. And the riverbed you are seeing is in cyanish color because of the moisture content, right? If there is no moisture, it would have been white. Dry soil would have been white wherever there is no this thing. Urban areas come in steel gray or greenish in color like here, right? So because they reflect equal proportion of red, green and blue, and they come in around more steel gray or greenish, you can say, more of greenish tinge you will see as the urban areas here. Right. So this is visually we are interpreting the image and extracting information about it, judging the significance. Now, the satellite data is captured in digital mode. They are basically digital images, right? So these can be processed with the help of a computer. They can be processed with the help of a computer. What happens is when we are doing visual interpretation, the visual interpretation is very subjective, based on the experience of the interpreter, based on the local knowledge of the interpreter, right, and based on the interpretation keys that are available. They are not repetitive. Something which one interpreter interprets may not be deduced by another interpreter because of his different local knowledge, different experience. But digital processing, when you do, if you apply an algorithm, it will always result in the same result. That means the outcome of a digital image processing will be repetitive, right? So we can do that means same, it will obtain the same result when one interpreter is doing the processing or the other interpreter is doing the processing, because it is the algorithm which takes over. So digital image processing is the computer processing of the digital images which are captured by the satellites, right? And we do it for removing the errors from the imagery, enhancing the imagery, and extracting useful information from the imagery. So that means we are doing the digital image processing for three basic functionalities. We are doing digital image processing for three basic functionalities. That is removal of errors, that is image restoration, image enhancement, which is improving the visual content of the image for visual image interpretation, and extracting useful information. That means utilizing the algorithm's capability to automatically categorize the imageries into different classes. Right? So this is a very short overview. I will show you the experiment, how we do the digital image processing, right? Various techniques of digital image processing. Now, before I go to the experiment, it is important that to reiterate that to extract meaningful information from remote sensing imagery, we usually use both the visual and the digital methods, right? Both are not mutually exclusive. Both methods are employed when we are extracting useful information from a remotely sensed imagery. So now with this short overview of theory, I will show you the experiment. I will show you the experiment by using a satellite imagery. In my experiment, I am using here a software called as IIRS Imagine. I'm using a software called as IIRS Imagine.
Yes, madam. Yes, madam. You can continue.
Yeah. Okay. Now, if you look, I have opened first to show you the various color composites. I have opened here a photograph, right, where you see the IRS selfie point, right? Those of you who have visited IRS, this is an IRS selfie point, and you can see the green color of the grass and the trees. Now, so the first experiment that I'm trying to show you is how we can change colors to identify different objects by changing the, okay, before that, IRS selfie point. Now, when I'm displaying a single grayscale image, right? Same image I'm showing you in grayscale and same image in color. So in a grayscale image, though you are seeing the bright and the dark objects, you cannot judge the different objects. You cannot judge whether the objects are the, like you can see if this is a green plant, right? The grass is green and the trees are green, but they are having different reflectances. So you cannot judge the significance of the different land uses in a grayscale image, right? That is why our color is important. That is, we are having a composite. Now, when we are having a composite, this is a true color composite. Whatever colors you see on the ground, same colors you are seeing on the in the imagery. Now, I can change these colors to show you the concept of false color composite. Now, whatever was captured in the red portion of spectrum was shown in red, green in green, and blue in blue. Right? Now, if I simply change the order, you see, now the colors have changed. The colors have changed, though you are still seeing the grass in greenery, right? The green, right? But the colors of your IRS selfie point, those who have visited, you know it is orange in color, and now you are seeing it as green. Now, if I simply change another option, 2 to 1, you see now the greenery has also changed to violet, to the purple shades, and your IRS selfie point has also changed. So first thing is that with a software, if you have an imagery, you can put it in different layers and you can judge the different objects. You can judge the significance of different objects in different colors. So with this concept, the satellite imagery was captured that we had more number of layers, more than what is the visible bands, right? In infrared and in the beyond the infrareds and beyond the violets. So not only the visible but beyond the visible portion also. Some objects get highlighted when you change their band combinations. They appear different from each other. Like for example, I will open the true color here. So this is the true color. Imagery for reference. And now coming to the satellite imagery. Okay, so this is a satellite imagery where I told you the red color indicates the vegetation because it's a false color composite. It is a false color composite. Here if you see, infrared band is displayed on red, the red on the green and the green on the blue. So this is a false color composite. Water body is dark blue to black. Riverbed you are seeing in cyanish. Agriculture areas in varying shades of pink, and you have the urban areas in steel gray or greenish areas, right? Now the spatial resolution that I've shown you here is 36.25 meter, and this is the reservoir, Assam reservoir, which I'm showing you here, right? Now this is 36.25 meter on list 2 sensor on both the IIRS 1A, 1B. Now same area I will show you in a list 3 image, right? A list 3 image, right? Spatial resolution now here is 23.5 meters. Now if you look at the details, I will zoom the portion of the reservoir. If you look at the details, here the reservoir looks very coarse. Where the canal reaches the reservoir also is not visible, but here details become finer. Right? Because the spatial resolution is more, and we are seeing the same bands, infrared, red and green. Right? So 36.25 meter resolution, 23.5 meter spatial resolution. Now increasing the spatial resolution, let's come to the 10 meter spatial resolution from the Sentinel series of satellites, which is not Indian, it is foreign satellites. So now if you compare, the details go on increasing. If you look at the reservoir, very finely you can see where the canal and the is entering the the confluence of the canal and the reservoir. You can start seeing the urban areas also, the water channels, right? So from 36.25 meter to 23.5 meters to 10 meter spatial resolution. This is imagery at 10 meter spatial resolution. Right? Now going finer, let me show you an imagery at 5.8 meter spatial resolution. This is my imagery at 5.8 meter spatial resolution. You can compare it with a 23.5 meter and a 10 meter spatial resolution. Even on the dam you can see the various objects right here. You can see. So 5.8 meter list 4 data on the ResourceSat 1-2 series of satellites. You can see the canal boundary is so finer here in the list 4 data and the canal boundary is little blurred, or the object is not so fine. So with the increasing spatial resolution, we are seeing the finer details. With increasing spatial resolution, we are seeing the finer details. Now, okay. Now coming to, let's say, in the list 3 Ponta, 23.5 meters, I have 4 bands. I have 4 bands here. Now I am showing you here infrared, red and green. We can make different combinations like 2, 3 and 1. So the color composite changes. Some objects get highlighted in this combination and some get highlighted in the other combination. That means based on how much the different objects reflect in different wavelength bands, they get highlighted in a particular band. They get highlighted in a particular band and so on. Now let me show you a very fine high resolution imagery. Now this imagery is from Cartosat series of satellite and its spatial resolution is 0.6 meters. Here you can see 0.6 spatial resolution image, and this is for the Dehradun area. Those of you who have visited, this is my FRI area, the FRI building, right? It is visible here. You can see other smaller buildings near the FRI, the different buildings of FRI campus, and the urban areas. The boundaries are so clear for different other buildings. So, and even some vehicles on the roads are visible in this Cartosat series of satellite, where spatial resolution is 0.6 meters. Okay. Now coming to a Sentinel series of satellite. Now Sentinel series of satellite, it has many different bands. I will show you the slide where I had listed the slides, the bands of the Sentinel. Here you can see Sentinel series of satellites. They have 12 bands. Some bands are at 10 meter spatial resolution, some bands are at 20 meter resolution, and some bands are at 60 meter spatial resolution. So I will show you the difference of those bands. Now first thing is, here it is also recording the blue portion of the spectrum, as you can see. So here it is also recording blue portion of the spectrum. Band 2 is blue, band 3 is green, and band 4 is red. So what you are seeing here is a true color composite, right? In near true color composite, you are seeing vegetation in green, right? Now some objects are still not very clear, which, like, I'll zoom some portion, and if you see, these are 10 meter spatial resolution. So if I want to use the infrared portion, I should use the band number 8. I should use the band number 8. Right. So I will put 8, band 8, band 4, and band 3. So this becomes my standard false color composite, and you can see the different trees come in different shades of red, right? Where in the original true color composite, you are seeing all vegetation as green. Now here you can you can see different intensities of red. So they are different type of trees, different density, different height, right? Different health. So by using the different portions of electromagnetic spectrum, the identification of objects become clear. Then now next is, we can use we can classify one of the images to make a land use land cover map. We can classify one of the image to make a land use land cover map. Right. So I will open the list to Ponta imagery. Okay. So, and we will classify this imagery to make a land use land cover map. To make a land use land cover map, I have to tell the software to what class is present. So I will mark training samples. I will mark training samples and classify this imagery. So first sample that I am marking is of water body. And in the signature editor, I will add it. And I say this is a water body. And I want to give it a green color, sorry, a blue color. So this is my water body. Then I want to add another class here, maybe forest. And forest, I want to give it a green color. Right. Now coming to another class, a riverbed I can take. And I will give it a white color. And I will take an urban area. I will give it a red color. And some agriculture areas I will take. Now agriculture areas of, there are 2-3 types of agricultures, one where there is no crop and one there is crop, so I will take a fallow agriculture area. Agriculture, type of agriculture, and I will give it a yellow color. So now with these samples, I'll just simply try to show you how to classify. So then I can do a supervised classification, output imagery. And I say classify. So the software will classify and make a land use land cover map out of my data set. So you see, it has made a land use land cover map out of my data set. It has classified it into the samples that I had given: water body, forest, agriculture area, urban area, and so on. So this is how we make a land use land cover map from the satellite imagery. Another important thing which I can show you is how to highlight a unique information from the imagery is by doing band ratioing. But I think I have not taught you that, so that will become too much detail. Okay, so I think this is sufficient. Now if you have any questions, you can ask. This is a very short time to show you experiments of both visual and digital analysis.